Hello everyone, today we'll be talking about atmospheric pressure and how atmospheric pressure relates to weather. So for this first lesson here, we're just going to read through and you can see the edits that I've done to put the words in the right place so you can fill out your own at home. So atmospheric pressure. So a scuba diver knows that deeper you go into water, the more pressure you'll feel. This is, if you dive underwater, you start to feel more pressure. You might even find this if you go to a pool and you swim to the bottom of the pool. You can feel that depth, that pressure on your eardrums usually. As you're going down underwater, all of the water that's above you has mass and therefore weight, and that weight causes a force on your body. And that force that you're feeling is pressure. Well, the same case exists in the air. So when you're on land, you're at the bottom of an ocean of air molecules. They're not water molecules, so they're a little bit lighter. They're in a different phase, so they're a lot denser, a lot less dense, but they are still above you and they are still weighing down on you. And this air has mass, and so therefore it has weight. The further down you go in this ocean of air, the more pressure you feel. So when we're in the bottom of a canyon, for example, you will feel more pressure. Or here, you can see in this little drawing they've done, this is sort of a canyon here. When you're down here, you have more air molecules that are affecting you. When you're up on top of the mountain, you'll actually have a little bit less. And if you go up a high enough mountain, you'll actually feel the difference in air pressure. If you're a mountain climber, then when you get close to the top of the mountain, you'll actually require an air tank or something to provide you with extra air at a high enough pressure that you can breathe. So since we live at the bottom of the troposphere, we experience the pressure caused by the weight of all the molecules in all the layers of the atmosphere. We also live in the most dense part of the atmosphere because the air at the bottom of the troposphere is compressed by the weight of all the air above it. When you raise your hand in the atmosphere, air flows around it. If you did not, you would have to lift the column of air above it. So what we're trying to say is that air is a gas. Gases flow and they take the shape of their containers. So when we move our hand through the air moves around our hand. We can't really feel the weight of the air so much, except when we compare it to other situations where it becomes more obvious. So you may know that the metric unit of force is the Newton. 1 Newton has about the same weight as an average apple. Now, 1 Pascal, which is the unit of pressure, has a weight of about 1/9 of an apple. So typically 1 Pascal is only about a ninth of a ninth of the weight of an apple. It's a very small unit of pressure. It's the same as having 1 Newton of force distributed over an area 1 meter area. So picture 1 apple, round it up into applesauce, and then spread that applesauce across 9 floor tiles. Typically, a floor tile in our class was a 1 by 1 foot floor tile. And so if you spread that applesauce thinly across it, that would represent the amount of pressure on the floor caused by the air, by 1 Pascal of air. 75% of the mass of the atmosphere is located in the troposphere. So in those first 10 kilometers, that's where 75% of the atmosphere's mass is. And then above that, you'll have above that, the atmosphere decreases. The atmosphere is most of 100 kilometers high. So why is such a high fraction of the mass located at the bottom? Well, this is an effect of gravity. Gravity is stronger as you get closer to the source of it. So maybe we will write that. So one effect is that gravity is strongest closer to the origin, so the Earth. And also, we also have an effect of energy, and energy causes gases to expand and become less dense. So as you heat up the air, it also expands, becomes less dense, floats upwards. So here's an example of what we can extract from all this. So if you were standing at sea level, all of the air above you would be about 100 kilograms of air molecules that are weighing down on you. Now this is air molecules weighing on air molecules weighing on air molecules, but when you're standing on Mount Everest, where you're at the top of the troposphere, then the column of air you have to lift is only 35 kilograms because it's 75% of the air is gone. So that means that the amount of air pressure is very much different here. So figure 2 shows that the Earth's atmosphere applies a much greater pressure to the floor. Standard atmospheric pressure, the pressure of 25 degrees dry air, is about 101,300 pascals, or more commonly 101.3 kilopascals. This is a unit that is used very often in calculations later on in your science career. So memorizing 101.3 kilopascals, not the worst idea. It's a pretty valuable unit. It is standard pressure at sea level in dry air. We don't perceive pressure because air is made of molecules that easily flow around us when we move, and the pressure is exerted vertically. Therefore, the pressure of the atmosphere essentially tries to squish us. But it doesn't push us forward, it doesn't push us backwards, it only pushes us down. And we don't get squished because our bodies are stronger than 101.3 kilopascals. The water in your body, in your cells, is enough to keep your cells fully inflated, even under this pressure. And we also have air in our bodies that pushes outwards with the same amount of pressure. So, however, we may experience side effects due to pressure changes when the pressure changes in the atmosphere, either due to altitude or to elevation. So moving around the globe, moving from the equator to the northern hemisphere or the southern hemisphere, you might notice some changes in how your body feels or the experience you're having. And also if you go vertically, so for example, riding on an elevator. If you take an elevator up to the top floor very quickly, you might notice some change in your eardrums. Or an airplane, for example, is very common for people to have their ears pop during an airplane ride. Even though we are usually oblivious to this tremendous pressure surrounding us, it can have dramatic effects in certain situations. If you can change the situation such that the pressure on the inside of an object is removed, like making a vacuum, then you'll see something happen where the pressure that is always pushing on us, if suddenly there's no force, no equal and opposite force on the inside of the object can collapse. And so here's an example where a tanker car has been collapsed by the outside pressure. So air pressure was pushing in on this tanker, and meanwhile there was no air pressure to push out. On a healthy tanker, that even if it's empty, if the empty tanker has air inside, the air pushes outwards with 101 kilopascals, and the air on the outside pushes down on it also at 101 kilopascals. But when you take the air out, so this is full of air, if we take the air out, or if we remove some of the air, so if we put vacuum, then there's no force on the inside, and there's only the force on the outside. So that air pressure from outside is still going to push down on the tanker, and it will collapse. So this is something that can happen if you're evacuating a tanker, or if you leave a tanker with the ability to where it heats up during the day. And as it heats up during the day, some of the air molecules escape because they get hot from this tanker being black and empty. So the black paint absorbs a lot of heat, heats up the air inside. The air escapes, and then if they seal the tanker up overnight by accident or whatever, when they seal the tanker up, it has less air in it than it had before, and a vacuum is formed, and the tanker can collapse in on itself. And we can do this with an aluminum can quite easily, and I will try to link a video of that aluminum can being crushed. It is described in at the end of this booklet. Now, atmospheric pressure and its relation to weather, well, we have seen that soil and water, they have different heat capacities. I don't know if we discussed this in a previous lesson. So, because of the difference in heat capacities, the ability to absorb heat, the Earth does not heat evenly. Thus, the Earth's atmosphere also does not heat evenly, because the Earth's atmosphere is heated by the ground, by what it's above. If it's above water, well, water absorbs a lot of heat. It has a high heat capacity. If it's above, so it doesn't share a lot of energy with the air above it. So the air above it will end up being cooler. If the air is above some hot sand, on the other hand, well, hot sand has a low heat capacity. It reflects a lot of heat. It gives off a lot of heat. So the air that's directly above a desert will become quite hot. And quite a bit hotter than if the same amount of sunlight was shining on a lake. So this warm air will rise, it will become less dense and lighter, and thus the atmospheric pressure in the area will be lower than normal. So when you heat up the air, you'll have a zone of low pressure. So high temperature, high temp equals low pressure. Okay. Cold air is more dense than warm air, and it tends to sink. In this situation, you'll create a region of high atmospheric pressure. There is a balloon demo that we did not do, but air tends to move from regions of high pressure to regions of low pressure. So if you, for example, were to provide a heat source in the room and put a balloon, you would find the balloon would move away from the heat source, because the heat source provides high pressure, low pressure, and or do I have that backwards? I guess the balloon would actually move towards the heat source, because that should be low pressure air. Although it might be warming up the balloon. I don't know what this demo was. We'll have to see what it is. We'll have to look into that. This moving air, so air tends to move from regions of high pressure to regions of low pressure. So this moving of air is commonly called wind. The greater the pressure difference, the stronger the winds. Remember, high temperature is the low pressure region. So we will see that air goes from a place where it's cold. The cold air will roll in to zones where it's warmer. So low temperature, let's just make sure we write this down. Low temperature equals high pressure. So this is going to contribute to one of the reasons why a wind might feel cold. You don't usually think of wind as being hot, and that's because the wind that is rolling in is a high pressure air, and that high pressure air will be lower temperature than the air around it. We will see too that these differing atmospheric pressures are also key to the formation of precipitation and to global air movement patterns. This is why barometric pressure, the atmospheric pressure measured with a barometer, is so important to meteorology, and is not only reported in weather forecasts, but also used to create forecasts. We actually have a classroom barometer. It's a little tabletop barometer, and it measures the temperature in that day, but it also measures the air pressure in the room. And even inside the building, simply measuring the air pressure of the air inside the building, it is able to predict, just with that one measurement and the temperature measurement, it can predict what the weather will be like the next day or later that day. And it does a pretty good job. With a single measurement, it can measure that sort of detail, just because the barometric pressure is so key to weather. So we might see maps like this. This will show zones of low and high pressure. You can see the L's over here and the H's over here for low and high pressure. And you can actually zoom in on these maps, and you can even these numbers have meaning as terms of what is the current pressure. Here's your 101 over here. There's a 101, so that's pretty normal pressure. You can see a 118, so a little bit higher over there, I would imagine. So these maps can tell us a lot about how temperature is moving. So they will often indicate high and low pressure systems on them. We can see here in this map, you can see a low pressure system drawn out here. And we can see the high pressure zones up here. And so high pressure means colder, and the low pressure would be warmer. And these arrows and things have meaning, and we'll discuss those in a later lesson. Here you can see these are these values that they're showing here, 1033. This is a high pressure zone because we said that it's 101.3 is the pressure at sea level. So this would be high pressure, and that's why we can see the H here. So it's high pressure zones, 103.2, and etc. So these maps are all sorts of maps, and they are very interesting to look at. They're complicated sometimes to look at, but we can work out some things about them. We can look and see, here's a low pressure zone here, so that would be a zone of hot air, and then another low pressure zone compared to the high pressure zone over here, where this would be cold air. So this is cold air, and we would expect that the cold air is going to start moving in one of these directions, usually following the curvature of the ground and sort of falling or rolling across the ground. So atmospheric pressure readings are collected from all over and are used to make surface analysis maps, and the lines show isobars, lines of equal atmospheric pressure. So each of these lines around that line is the same atmospheric pressure. So for example here, we can see a dark line here that is labeled as 1024. So that'd be 102.4 kilopascals. And that would be all along that line that it would be 102 kilopascals. And probably these dotted lines are wind, is my guess. Okay. Hurricanes and other storms are created by very low pressure systems. So low pressure, what does that mean? Think about that again. A low pressure system means high temperature. And often these extreme weather conditions will be caused by the interface between a high pressure system and a low pressure system, and where that air mixes. And that will cause all sorts of, that'll often be the cause of these extreme conditions. Okay, I will try to find you a video of the aluminum can demo that you can look at in this posted with this video on our Google Classroom. And otherwise, have yourselves a great day, and we'll see you in our next video.